Hello again. Welcome to the latest Lockdown Science webinar. This time I'm going to talk about the physics of the impossible. The impossible, what a wonderful word. What do we mean by impossible? Okay, impossible. Impossible, things that we cannot do. What makes things impossible? Well, either we don't know how to do them, or we don't think that science will actually let us do them. And that immediately splits the impossible into two different types. Actually, we can split it into more than two different types, and that's how I'm going to approach today's topic. I'm going to talk about what are these different types of impossibility. Then we'll look at our type 1, type 2, and type 3 impossibilities. And then I've got a whole bunch of references, as you would probably imagine. Okay, so what are our different types of impossibility? Well, science fiction's full of them. Science fiction has got huge numbers of physically impossible things. Faster than light travel, the time travel, telepathy, teleportation, cloaking devices, Death Stars, you name it, we can do it. Science fiction is where we explore the impossible. We take an idea which is impossible and we see what it implies. And of course, some of these impossibilities are just such fun to play with. We then build an entire background universe based upon these impossible things no longer being impossible. Now, our definition of impossible actually has varied over time. If you consider flight, your medieval person in the street would think human beings cannot fly. If you ignore the occasional mad monk, that is. There were a couple of mad monks who had a go at flying, normally from castle walls, but they didn't really succeed very well. Until 1783, humans do not fly. Along come the Montgolfier brothers and build a hot air balloon. Now, okay, there are some records of large man-capable kites before that, but they're not very solid records. We have really solid evidence of the Montgolfier brothers and their first hot air balloon in 1783. By the time we hit the 19th century, we have gliders, George Cayley. 1901, the first powered manned flight. Yeah, you thought it was the Wright brothers. No, it wasn't. It was a German immigrant to the United States, Gustav Weisskopf, or Gustav Whitehead as he became known. Yeah, obviously I know about this one. But because he was a German immigrant and not a good old American, it was the Wright brothers who got all of the publicity in 1903. But the point is, at the turn of the 20th century, powered manned flight was impossible. By the turn of the 21st century, we had not only done powered manned flight, we had done manned orbital flight, and we had done interplanetary flight. 1969, Neil Armstrong walks on the surface of another planet. Some point this century, we will have someone walking on Mars. I'm not convinced it'll be before 2030, but it will happen. I hope before 2050. So all of these things were thought to be impossible. So what we think of as impossible is therefore a function of time. It depends very much on what the state is of physics at any moment in time. So if we allow for impossible being time limited, how are we going to define time limited impossibilities? How are we going to decide on what is really, really impossible? Well, Michio Kaku wrote a brilliant book called The Physics of the Impossible, which introduces all of this. Now, I've put the reference to the book at the end. It is a great fun read. Of course, he's now 10 years out of date, but it's still a great book. Pick up. He divides impossibilities into 3 types. Type 1, impossible today, but does not break the known laws of physics. In other words, it's something that we may be able to do within the next couple of 100 years. Think of it as these are not so much physics problems as these are engineering problems. Our type 2 impossibilities are the ones that are really at the edge of our understanding of physics. Those bits which the physics is cutting edge and we're not entirely certain if we understand it or not yet. So there's a lot of stuff working with gravity in particular that goes into this. Well, we've got an idea of how it works, but we've no idea how to play with it yet. So we think we know how to do it, but it's not something we're going to be able to do in the near future. And then our type 3 impossibility is the thing that grossly violates the known laws of physics. This is your classic things like perpetual motion. So these are the things we're pretty sure that the physics works, and this breaks one of our most basic laws. So I'm going to look at the 3 of these in turn. So let's start off with our type 1 impossibilities. Impossible today, but do not break the known laws of physics. Invisibility, ray guns, robots, starships, force fields, teleportation, telepathy, telekinesis. Absolutely classic science fiction stuff. This is the stuff that's been within science fiction for 100 years. People have imagined these things and thought, yeah, we can do these. So how are we going to actually deal with them? Let's start off with invisibility. Yep, we can do this. Well, we understand how to do this. Closest we've got are metamaterials, and metamaterials are really quite cool things, because what happens is you fire a beam of light at it and the physical material itself forces the light to pass around the object and then focus back into the original beam of light. So the diagram on the left is showing an incoming beam from the left. The blue thing is the metamaterial shell, and it is forcing the light beams around the red object and then refocusing them again on the outside. So if you were standing on either side of that red ball, you wouldn't see it, because as far as you're concerned, the light just came straight from the left to the right. Now, scientists have got pretty good at building these things. They've got them working for radio, they've got them working for microwave, they have got them working for visible light, but one of the problems you have with visible light is you've got quite a wide range of wavelengths, and many metamaterials have to be tuned to the wavelength that you want to refract. Now, the really cool one with this is they've got it working for earthquakes. There are serious plans for building structures offshore in earthquake-prone regions, which would deflect and refract P waves and S waves, thus providing some protection for the coastal regions. So it's a really cool concept, and because the wavelengths of the earthquakes are quite large, you do it with 10-meter diameter pillars. Because what you're doing is you're building a metamaterial structure, and for these structures to work, the fine detail must be smaller than the wavelength of the light you're working with. And this is why they started off with radio and microwave, because they were dealing with reasonably long wavelengths, that they could build devices that had surface variations on a scale that would affect these. Visible light is much more difficult because you're dealing with much shorter wavelengths. We have ray guns. Yeah, we could do ray guns, not a problem. Ray guns, lasers, phasers, call them what you like. We've got them, we're using them. We have battlefield laser systems such as the Zeus, which is used for mine clearance. We have the phaser. Yeah, not that the US military likes science fiction at all. No, no, no. The personnel halting and stimulation response. This is a handgun, or a handheld weapon anyway, designed by the US Air Force. And what it does is it effectively heats up the surface of your skin to a point where it feels uncomfortable, so you back away. Yeah, we've got that. There's the ADS, active denial system, the heat ray, the US Air Force and indeed the US Navy have been playing about with airborne laser systems for quite a while. The Chinese have shipboard laser systems. Shipboard systems are brilliant for this because if you're shipboard, you have plenty of space for your power supply. Big problem with any ray gun, shall we say, is the power supply that you need. Now, even the UK's got one. We've got the Dragonfire system, but again, it's all naval mounted because on a naval vessel, you can stick in a couple of nuclear reactors if you really want to. The big issue with any ray gun approach is your power supply. So we're not really at the point where we've got proper handheld ray guns, phasers, lasers. Partly because battery technology is not far advanced enough. We have huge problems with battery technology. We just can't store enough power within the system. And until we get either very small, very powerful energy supplies, or we really up the energy storage capacity of batteries, we're not going to get proper phasers, laser guns. Having said that, give us 100 years, no problem. We'll get the tech working. There's a lot of research being done in that area. Robots. Well, not quite C-3PO, but robots in general are reasonably common. Now, 1961, General Motors introduced manufacturing robots. We now have a lot of manufacturing is done by robot. What we tend to think of in science fiction when we view robots is we're thinking of humanoid robots, be it Robbie the Robot, C-3PO, pick your pick. If we want them to be totally humanoid, we're going towards the Cylon side, then we're getting there. The big problem is not building the robot, it's the computing behind the robot. It's the AI. Now, AI is a huge problem in computer science. It's so big that actually we haven't even really defined the problem yet. We use the term AI because everyone knows AI means artificial intelligence, and AI as a term has been so misused because people think, oh, it means robots like C3PO, it's thinking computers. It has been misused so much that those of us who work in data mining, the application of artificial intelligence to data mining, things like that, we no longer actually call it AI. We call it machine learning because AI has this big, it's a big problem with what the public think AI is compared to what the engineers think AI is. Now, if you want to build a C3PO, take your pick, something that can interact with humans in a human-like manner, you can either take the top-down approach and teach it everything it needs to know. That's the way we do it with manufacturing robots. We work out exactly what motions they need to perform, and we teach them every motion that they need to do. Or you can take the bottom-up approach and let it learn from scratch. We're seeing this quite a lot now with things like the dog bots from Boston, the ones that they've worked out how to open doors. And in these cases, what you do is you set it a problem and let it start wiggling its appendages about and work out what works and what doesn't work. So that's a huge research field. Will we get there in the long term? Yes, we will be able to come up with something that simulates a human well enough that they can communicate with us in a 3PO-like manner. Not a problem. It's going to take time. We're going to have issues with miniaturization, but it's going to happen. It's not a big problem. Starships. Well, as long as they're not faster than light, we can do great things. 1958, Project Orion. Earth to Mars in 2 weeks. Earth to Alpha Centauri, 44 years. Could have been done in the 60s. Later on in the ongoing lockdown science webinars, I'll do my Project Orion talk, which will go into this in much more detail. Basically, Project Orion was you take a vessel and then you throw nuclear fission devices out of the back end, you explode them, and the explosion will push your starship in the direction you want it to go. Great idea. Bit messy, but very, very fast. The next serious investigation was Project Daedalus. Again, nuclear powered, but this time fusion powered. Okay, we've got a problem. We haven't got fusion working yet. This is why I say this is a near future solution. Now, okay, we know fusion power is 30 years away and has been 30 years away for at least the last 50 years. But if we can get the fusion working, then we can go interstellar. We could send a probe to Barnard's star in about 50 years. So that's a perfectly good long-term plan. Project Longshot, late 1980s, fission fusion powered, small interstellar probe, Earth to Alpha Centauri in a century. Can we plan for a century as a species? Sometimes I don't think we can plan for more than 48 hours. It would take a United Nations level organization to do it, but technologically we could probably have a go. The latest of the Starship suggestions is Breakthrough Starshot, which is currently active, 2016, and they've gone for the solar sail approach, and instead of sending a large object that requires a lot of power to move it, you have a solar sail and a nanocraft, so a very, very small, very, very light device. This, they reckon we could get to Alpha Centauri in 20 years, which of course means Proxima Centauri and its planets in a bit less than 20 years. And this is such a cool, sexy idea that I really wish we could get a bit more on board with this one. Can we do force fields? Yes, we can. And we've had them since the mid-1990s. Now, this assumes that we're sticking with the 4 currently known forces. So, electromagnetism, weak field, weak force, strong force, gravitational. Basically, yeah, we can do these things. The plasma window was patented mid-90s by Brookhaven, and the idea is you've got a hot plasma on one side of a magnetic and electric field, and you can manipulate these fields such that the plasma can be contained in a very small area, or it can be kept on one side of the field, and this will allow the radiation to go through the field, but it won't allow the atoms to go through the field. And yes, people have looked at this and thought, you know, we could build lightsabers using this. And they have done serious work on using this as a cutting tool. Plasma windows are great. They don't let atoms go through. They only let photons go through, which means that you could use it as a defensive force field. So it will stop projectiles, but not laser weapons. So it's not going to stop your phasers, but it will hit it will stop missiles. And you could do it by layering a plasma window on top of a metamaterial. And in fact, Boeing were granted a patent on this in 2015, which is literally a force field shield for an aircraft. Yeah, cool stuff. Now, if you can shape the fields, then you can build your lightsabers. Great, not a problem. Problem we have with this is, as with the laser weapons, the power requirement. You know, to have something the power of a lightsaber with the power supply in a handle that small, that's fairly impressive energy management. But that's not the only type of force field that we can build. We also have tractor repulsor force fields. So your classic tractor beam or your repulsor beam. If you think about it, maglev is a repulsor field. You have got magnetic fields that repel each other. So you can levitate things. We've even levitated frogs. Basically, everything is diamagnetic. So it'll repel magnetic fields. And if you've got a large enough magnetic field, you can levitate a living being. mainly because we're basically water. Now, they've shown this with frogs. You could do it to a human being, but again, the power support source required is quite high, and the field strength, let's just say, if you were to do it to a male, you'd want to make sure that he'd done any breeding he wanted to do first. So, yeah, we can do it, but you may not really want to do it. We can also do acoustic tractor beams. So you have sound waves interfering with each other, and you can move small objects using these devices. I have even seen plans for building a small acoustic tractor beam using your 3D printer. Again, pretty cool stuff. Now we get to the big three at the end, the psionics stuff. Yeah, well, this doesn't necessarily work, psionics or otherwise. Teleportation we see all over the place. Star Trek does it, Blake Seven does it. You know, we've got it all over. Science fiction teleportation takes an object and it does it in one of two ways. It either identifies the location of every atom in an object, converts that into energy, then reassembles them in a new location. Bit of a problem. Heisenberg doesn't really fit with this. Never mind the ethical issues of, is it the same person that comes out at the other end? Or if you send if you send a person through a transporter for the first time, are you actually killing them? The other solution is to force the entire object to quantum tunnel from your current location to your new location. Both of these are on the, let's say they're on the fringe of modern science, but there is a real world type of teleportation that we're starting to play with, and this is quantum teleportation. The difference between modern quantum teleportation and science fiction teleportation is that real world teleportation transfers information. What it does is it takes information about the state of a particle, generally something that's entangled with something else. We get involved with quantum entanglement for all of this, and it transfers the state information of one particle to another particle. Now, this was originally suggested in 1993. It was confirmed in 1997, and they've got it working over huge distances. And it does sort of allow FTL information transfer, but some of the information is subliminal, and yeah, you can kind of imagine me waving my hands about at this point. The really cool thing about this is that it's all linked up to quantum entanglement, and the latest thinking is that quantum entanglement may all be mediated by wormholes. Now, when I first read that paper, I was quite blown away by it. Yeah, watch this space in terms of more information on that one eventually. So again, it's something that we can do some of it, or we will be able to do some of it in the next couple of 100 years, but it's not really the full science fiction version of it. Here is our basic quantum teleportation state. What we have is photon A, which has a particular quantum state. A and B are entangled, and we can change the state of A, and if we change the state of A, it will change the state of B, which is quite fun. I won't go into the detail on the quantum stuff, don't worry. Telepathy, another impossibility. Well, yes, sort of. We've been doing research into telepathy and remote viewing since the 1940s, in particular, the CIA's Stargate and MK Ultra programs, looking at goats, that sort of thing. But it was all very much inconclusive. Again, we can't come up with a good physics-based reason as to how it would work, unless, of course, we invoke quantum. But invoking quantum is kind of hand-waving, very, very fuzzy at the best of times. We can do machine-assisted telepathy. We could take MRIs and read thoughts using handheld devices. I've put lie detector techniques in because you can do lie detectors, but only if you're going to use an MRI. You can't do lie detectors by measuring sweat. People are very, very good at faking those. So you can only really do it if you've got MRI brain imaging systems. And the way you do it is you detect specific forms of activity in specific areas of the brain. Fantastic, no problem. So this is now used, yes, I say now used, to detect people, or to look at people who are in vegetative states, persistent vegetative states, to see if they can respond to questions. And the standard one is imagine that you are playing tennis. Don't know why they opted for that. And they found that they can communicate with some people who they thought were in persistent vegetative states by detecting changes in brain activity due to responses to questions. They haven't really been able to decode it, although, of course, there is a lot of discussion going on at present about the, I can't remember whose it is it Jeff Bezos has the latest one where you're going to stick lots and lots of little fibers into the back of your head, and then you can just plug in, you can just jack into it. It is real neuromancer style stuff. We can also do it with transcranial magnetic stimulation, which is a system whereby you manipulate the magnetic field on top of the head or just over a particular area of the brain. And they have performed experiments with this that allows people to see colours or to get sensations from other people. So this is really the basis of synthetic telepathy. So it is telepathy that is mediated via technology. 1960s, you could do EEG signals of alpha waves to generate Morse code. Nowadays, you can do internet transmission of EEG signals. They did that with taking the EEG pattern of a monkey performing a task and then sending it over the internet to another monkey whose arms were forced to perform the same tasks. You've got the signals sent over the internet into the brain, and the brain then interpreted those signals, sent them out along the arm muscles. There you go. The monkey does the same thing. All of these synthetic approaches are perfectly possible. We are going to see them in the next while. It's all linked into things like intelligent smart limbs. So you can actually control them using your own brain signals, nervous system signals. It's all related to that area. So synthetic telepathy is going to become a big thing. Natural telepathy, as I said, we can't do it without invoking quantum. Telekinesis, again, same thing. This is where your electronic limbs come in. You're controlling wheelchairs. You can do it via brain-computer interfaces. They were testing these things out in the 1980s, and it is now becoming not common, but I have seen these systems working. It's a lot easier to do it with implanted electrodes than to do it with EEG, but they have used both systems. They have also used such systems for fighter aircraft. They aren't using them in practice, but again, back in the 1980s, the USAF were very definitely looking at thought-controlled aircraft. Yes, Firefox was a fun film and an interesting book, but they were really looking at that as synthetic telepathy, synthetic telekinesis. Why do I know all of this? Well, it does link in quite nicely with the eye tracking, because if you can look at something and think fire, it's probably a lot faster than looking at something and then pressing the button to select fire. So it does all tie into the work I did on my PhD. So those are the manageable with current technology. The big problems we tend to find with them is energy generation and energy storage. We're pretty good at generating energy. We can generate quite a lot of it. If you imagine the amount of energy that the fusion research centres need to use, admittedly only for short periods of time, but it's a lot of energy. We can actually generate quite a lot of energy, but we're not very good at generating it in small devices, and we're really not any good at storing it. So what we need to do in order to make these type 1 impossibilities much more practical is expand the amount of energy that's available to us. If we can do that, then we can do an awful lot of interesting stuff. So this means that we would like to be able to set some sort of scale on how much energy is available, because the technology available to anything is dependent upon the energy available. Think what happened with the Industrial Revolution. We got steel, and we got steel in large amounts because we went from using wood as a standard fuel source to using coal as a standard fuel source. Same thing will happen. We've now got to a point where we're generating a huge amount of energy, but we're moving towards generating ever larger amounts. Right now, we are what we would term a Kardashev level 0 civilization. Now, Kardashev came up with 3, possibly 4, or 3 civilization levels based upon their ability to use the energy in the environment around them. And the different levels define the size of the environment that they can control. Sorry, it's 4 levels. It was extended to 5 later, and I'll talk about that later on. So Carl Sagan calculated that we're at about 0.7. We're now at about 0.75 because our use of renewables has increased this. So we are at the point where we're pretty good. We're getting about 0.75 of a planet's worth. of energy. 0.75 of all of the energy available to the planet. A level 1 civilization has total access, total control over all energy available on the planet, about 10 to the 17 watts. That's the equivalent of thinking, okay, well, every single photon that arrives on the planet from the sun, we can harness that for energy usage purposes. Now, when will we get to that? Predictions vary, but we're looking at 22nd, 23rd centuries. We're not doing too badly, but it does require a significant investment to get up to level 1. Level 2 takes this, well, I was going to say an order of magnitude further, a number of orders of magnitude further. This is now saying a level 2 society can control the energy resources of a stellar system. Now, stellar system means pretty much every photon that the sun emits we can use for energy purposes. Now, this is a very positive thought, but we're not going to get there for a while. The earliest predictions for this that I've seen are 2200, and that's incredibly optimistic. 2700 is possibly more likely. It, of course, requires a lot more going out into space and so forth. But if you do go out into the solar system, if you are working on all of the different planets, yes, the amount of energy available to you is so much higher. And with more energy comes more technology. Level 3 is the scary level of galactic level energy control, 10 to the 37 watts. Again, very optimistic 5 to 8,000 years, or 3 to 5,000 years in the future. Again, I think that's incredibly optimistic. This is the idea that we could take the Milky Way galaxy and we could harness all of its power. I don't think we're going to get there for a while. But if we can harness all of its power, what can we do with it? Well, this is where we start getting into type 2 impossibilities, because all of our type 2 impossibilities are going to require a hell of a lot of power behind them. We will need to be, at the very least, a level 1 society, preferably a level 2 society, if we want to get any of these things working. And the 3 classics in here: faster than light travel, time travel, and parallel universes. I'm not discarding any of these as being totally impossible. Current physics understanding suggests that actually all of these things are possible, but they're just going to take a hell of a lot of energy. So, starting off with faster than light travel. We have relativity, and relativity is great science in that it gives you lots of ways to prove it wrong, but so far no one's managed to do that. So if we want to do FTL travel, then we have to find a loophole in relativity, or we have to replace relativity with something. Both of those are really exciting prospects. So, loophole the first. General relativity tells us that no object with mass can travel at the speed of light. The operative word there is at the speed of light, not beyond the speed of light. It requires an infinite amount of energy to accelerate a mass to the speed of light, but once you're beyond it, then the energy falls away. This is probably a trick of the mathematics. But right now, that's a definite loophole. The second loophole we have is, well, instead of moving faster than light, instead of taking you to a different point in space-time, why don't you move a different point in space-time closer to you? In other words, you can stretch space. Now, space-time itself can move faster than light because the things within it are the things that are limited. Now, we know that space-time can move faster than light, according to our current theory of inflation. The beginning of the universe, just after the Big Bang, the universe grew at such an incredible speed. It was faster than light, but given that we measure light as being traveling through a particular medium, particular vacuum, light would still travel at the speed of light in the medium of space-time, but it would be space-time itself that was moving. So you can apply this to a starship drive by stretching the space behind you and squeezing the space in front of you. And this was originally proposed by Alcubierre in 1984. And this has been the subject of so many research papers since then, because again, it's such a really cool idea. NASA had been seriously investigating this. We see multiple different designs for Alcubierre spacecraft. There are significant problems, particularly with things like Hawking radiation, with negative energy, but NASA likes the idea enough that they are still looking at it. The problem, the mathematical problem is that, as is the case with a lot of these things, including time travel, wormholes and so forth, they are calculated backwards. In other words, you find a solution to the equations of general relativity, and then you kind of tweak the maths and see if you can make it fit. So it does rely very much on our current understanding of general relativity. Now, we know that our current understanding of general relativity is limited because we have not yet been able to marry together general relativity and quantum mechanics. So when I said we have to find loopholes in relativity or replace it, we will replace general relativity in time. It's just we can't do it yet. Another loophole, the wormhole approach. Rip space. Rip a hole in space-time and squeeze through. Problem is, it needs a huge amount of energy. We are very definitely talking level 2 civilization here. It then needs a lot of energy to keep it open. Now, unfortunately, we need lots of positive energy to get it open and lots of negative energy to keep it open. Negative energy does exist. We can generate it using Casimir effect. Casimir effect is an example of this, where you can get things to be pulled together by negative energy. It has problems as well, because any light falling into a wormhole is blue shifted, infinitely so. But the energy available to a Type 3 civilization may be able to do that. Now, I said that general relativity is going to be replaced. We have no idea what it will be replaced by yet. We've got a number of alternatives: loop quantum gravity, string theory, modified Newtonian dynamics, scalar vector tensor gravity, lots and lots of ideas, lots and lots of things where theoretical physicists have said, I wonder what happens if. Right now, who knows? We really have no idea which way is going to be the way to an even more accurate model of reality than general relativity. Now, general relativity also allows for time travel. The most obvious one is time dilation. We're always doing time travel, just on a very small, very, very small scale. If you fly from London to Edinburgh, then no problem. You do the whole time dilation things, you just don't do it very much. They have measured time dilation in the International Space Station, and general relativity is holding very nicely. Basically, with time dilation, the faster you move, the shorter your time is compared to the time for people not moving. So if you're flying from London to Edinburgh, you will age a fraction of a second less than someone who isn't flying from London to Edinburgh. Now, general relativity allows for time travel on a much larger scale, but it doesn't take any of the quantum effects into account. And this is another one of these issues where until we get general relativity and quantum mechanics merged, we're going to have problems. Now, the first solution for time travel was Gödel, who defined a rotating universe model in the late 1940s. The better known one is Tipler's infinitely long cylinder. If you have an infinitely long, very heavy cylinder and you rotate it at very high speeds, you start dragging space-time around with it, and this allows you to do time travel, which is quite cool. It's basically the Star Trek let's go round the sun very, very fast approach. The idea that you can do time travel by going at high speed around a large gravitational object comes from Tipler's cylinder theory of time travel. It also explains the idea of why, if you want to go back in time, you want to go the other direction in time, you go back in the other direction. Again, science fiction picks up on science. Very nice. The next big theory was Kip Thorne's black hole wormhole theory, 1988. If you want to get that in a nicely digestible form, I can recommend Black Holes, White Holes and Wormholes. Stick it in Amazon. It's an excellent book. Gott also looked at it with cosmic strings. Cosmic strings, again, takes Tipler's idea a bit further. But, you know, yeah, time travel theoretically looks perfectly reasonable. Hawking wasn't happy on this. Hawking really did not want time travel to work and suggested the chronological protection conjecture. In other words, there was something that made time travel impossible, or as he put it, makes the universe safe for historians. That was 1992. Before he died, Hawking eventually came to terms with the idea that, you know, time travel may be possible. It may work, but it's not going to be practical because the energy requirement is so high. So again, we're back to energy being the important basis for all of these impossibilities. It might be practical for a type 3 civilization, one that controls galactic levels of power, to be able to do this. Now, Kip Thorne's method, I did tell you we have the orange, yellow and black photo. Kip Thorne's method requires a large black hole that is rotating. The reason it is large is it avoids the excessive tidal forces. You don't want to be spaghettified as much. It has to be rotating because if it's a rotating singularity, then rather than having a point singularity at the center, it has a toroidal singularity at the center. So the idea is you can go into the black hole, you can fall towards the singularity, and instead of going splat on the surface of the singularity when you reach the middle, you're going to go through the hole and come out on the other side. Yeah, whoa. The maths works. M87 has one of these. It has what looks to be a large and rotating singularity. We know this because we've measured it. The problem is it's sufficiently far away that going there and having a look at it and testing it is going to be a bit challenging. We don't yet have the data from Sagittarius A star, but I know that they are working on getting that data out. We got the first pictures of the M87 black hole because it's much more easily visible than Sagittarius A star. There isn't as much crack between us and it. So in theory, yes, we could time travel using a black hole. Gravity, the film, is not unreasonable. And in fact, Kip Thorne was one of the scientific advisors on the film. The basic premise is workable. Of course, once you start talking about going through black holes and out through the other side of it, you're starting to think of things like parallel universes. What do you come out at on the other side? Well, what can we look at with parallel universes? We can think of hyperspaces. Our normal space has three spatial dimensions and one temporal dimension. We've got height, width, depth as our spatial, and then we have time as our temporal. And there are a lot of string theories or brane theories that postulate up to 10 or 11 dimensions. Again, this is the theoretical physicists having fun and games with the maths. We have no idea if we can show any of these to be possible, never mind show that they can exist. Some of our theories allow us to have multiple temporal dimensions, which means that we can divide space into space-like space, where you can move anywhere you like in the spatial dimensions, but you're always going in one dimension in the same direction towards the future in time. Or you can have time-like spaces where you can move anywhere you like in time, but you're always moving in the same direction in space. Best example of this is outside of the event horizon of a black hole, which is a space-like space. We can move anywhere we like in space, but we're always going forward in time. But if you fall into the event horizon, then the theory, one of Thorne's theories suggests that you can move anywhere you like in time, but you're always moving in the same direction in space, i.e. towards the singularity. And this was beautifully illustrated by gravity, where you have, once he gets into the black hole, he's allowed to move through time any way he fancied. I thought that was a really nice visualization in the film. Now, in theory, if we could access one or more of these other dimensions, we may be able to do faster than light travel in our dimensions possible by effectively taking a shortcut. It's the idea of the wormhole. The wormhole allows us to take a shortcut between our bit of space to another bit of space. And if brane theory is correct and that we're on the surface of a brane, we may be able to rip through the brane and access the surface of an adjacent brane. Again, the energy required for this is going to be phenomenal. Type 3 civilization stuff. But the physics is quite cool. We have multiverses. Now, there are lots of different definitions of a multiverse. Can we get there? Well, what multiverses do we have? We have the classic science fiction parallel universe, the Starfleet, the Star Trek parallel universe, which has been used used with such great glee by Discovery. We have multiverses that may exist through the vagaries of quantum mechanics. In other words, every time you make a decision, the universe splits in two, and in one universe you made that decision, in the other universe you made the other decision. I think this is a situation where we really don't understand the maths, because again, the energy requirement is just horrendous for that sort of thing. Quantum mechanics is a problem because this is all quantum stuff. Now, what you kind of have to remember about quantum mechanics is that we don't really understand it properly. Most physicists will look at quantum mechanics and view it as it's a really good mathematical model for making predictions. It's the shut up and calculate approach. All of this comes out of the Copenhagen model that basically says, okay, unless you make a measurement of something, the system will exist in a superposition of states, but when you make that measurement, you'll collapse it into a single state. The Everett approach said, no, it doesn't collapse into a single state. Both states continue existing. And this is where you get your universe splitting due to different decisions. And if you can access these universes that split due to different decisions being taken, then if you can manipulate the quantum probabilities, you may be able to access these things. Again, the energy required will be huge. Now, all of these things represent things that are big topics in physics right now. We could wake up tomorrow morning to the news that someone has a fantastic new theory of physics that changes everything. And to be honest, it would be absolutely wonderful if we did, because we need some cheerful news at present. New physics, as it's known, could quite easily transform any one of these type 1, type 2, even type 3 impossibilities into, yeah, sure, practical problems. It's just an engineering problem. But even if the new physics pops up, we're going to have significant energy requirements. We don't fully understand thermodynamics yet. We certainly cannot link thermodynamics in with relativity and with quantum mechanics yet. There are issues. There are some theories that say you might be able to do this via information science, but linking some of the energy stuff to it, it's just not working yet. So in the same way that in 1782, it was impossible for a man to fly, and in 1783, it was suddenly possible, we could have exactly the same situation at any point in the near future. Now, the things that we don't expect to be broken are the things that are part of what we think of as fairly basic settled physics. Now, I've just mentioned thermodynamics. Perpetual motion machines link into this. The perpetual motion machine is the thing that we're pretty sure you're not going to be able to build. Now, lots of people have suggested how to build a perpetual motion machine, but they all break the laws of thermodynamics. The point of a perpetual motion machine is once you start it running, it keeps running no matter what. It doesn't lose energy at all. It will just keep on going. And all of these wonderful theories that allow, all of these wonderful theoretical perpetual motion machines break one of the three laws. So the first kind of perpetual motion machine will break the first law by producing work without needing input required. In other words, the first law, energy cannot be created nor destroyed, only transformed. It creates energy from nowhere. Energy appears by magic to keep it working. The second type of perpetual motion machine breaks the second law, hot things get cooler, by converting thermal energy into work. And the third kind has no friction or other forces. And unless we can access energy from another universe, these are really impossible, unless physics changes. And as I just said, we're a bit iffy about some little bits of thermodynamics. And if we have access to energy from another universe, that's going to take us up to the level 4 on the Kardashev scale, complete control over an entire universe's energy, which would be fun. Here is an early model of a perpetual motion machine. Leonardo da Vinci designed several, and the idea is once you start it spinning, the blocks click over, and that motion, the weight moving to the right-hand side of the wheel forces it to go down. But of course, this isn't a perpetual motion machine because you have friction in all of the hinges. So it doesn't quite work. So I've talked about lots of things that are impossible, and or lots of things that for most of humanity's existence we have thought impossible. Some of them are looking a bit fringe now. They're beginning to look, well, you know, maybe we could do it. Because what is impossible is very much defined by what is our current understanding of physics, what is our current understanding of the universe. And when we're really thinking about impossible things, Clarke's laws are a very, very good reference point. Now, Clarke's laws state that when a distinguished but elderly scientist states that something is possible, he is almost certainly right. When he states that something is impossible, he is probably wrong. He, she, or it, of course. The only way of discovering the limits of the possible is to venture a little way past them into the impossible. And of course, the most famous of Clarke's laws, any sufficiently advanced technology is indistinguishable from magic. Absolutely. If you think about it, how many times have you seen, or have you had conversations with people who don't use technology as much as you do, who say, oh, it's magic. The technology we use day to day is magic to someone 50 years ago. Fantastic stuff. So when we talk about the impossible, we have to remember that it is relative to our knowledge and the time in which we live. What is impossible now may not be impossible in 10 years' time, which is one of the really cool things about science. So lots and lots of references this time, although they're all web references. And I think they're still out there. A couple of them may have disappeared, I hope not. But an assortment of places, yes, Wikipedia. Wikipedia is brilliant. It gives you basic descriptions of things and all of the source material nowadays. It's no good as a primary reference, but it's a great starting point. an assortment of places, Alcubierre drives, space and time warps, and so on. And I would also recommend Michio Kaku's original book, Physics of the Impossible, available on Amazon and at other good bookshops, although possibly not right now. 10 years old, but well worth a read. So I should call that a day at this point and stop recording.